Yeah. So these were designed to actually handle text of various variable size, or input of variable length and output of variable length, like it is typical for language translation problems, and also for generation of text, and which is basically the same question. So you have an input pattern in form of text, or many input patterns. You train your model on this input and some related output. Yeah? So if you have a long text, you can use one sentence as input, one as output, or you can train the model to produce output. If you have translations, you can train the model on the translation of the sentence. In principle, it's the same concept behind. Yeah. So these approaches, like they've been studied 10 years ago, they actually focused on generating variable length content from variable length input. And to handle that, they used, or sometimes we still use, of course, we still use this kind of encoder-decoder structure. So an encoder is a deep neural network that actually encodes a variable length input into a vector of fixed size. And the decoder does the inverse. So it decodes a vector of a fixed size into a variable length output sequence. And as I said, it originally was proposed for language, for translation, but language translation, but there are many other applications where these kind of architectures can be used, not only in natural language processing, but also for handling data of other kind. For example, there's this idea of an autoencoder, which we could use to handle non-periodic measurements of any kind, like a sensor or a machine or something. So the general concept can be used for other types of input sequences as well. It doesn't have to be text. It could be measurements and movements of an actor in a robot or whatever as well. Because these for the model, it doesn't make a difference. It's always numbers. So the input is numbers, the output is numbers, and how we interpret it, how we use it for our application. Is it to transform it into text? We have an embedding, convert it to text, or we have a machine that uses it. In principle, it does not make a difference for the deep neural network. So that's the basic idea. We had a short look on that last time. I will not go to too much detail, but we could have a look at the model structure, and just to make it a bit more clear. So these boxes are usually some kind of recurrent neural network. A recurrent neural network is a network where the output is fed back into the input. So we have some implicit feedback loop here. In the practice, of course, it might be a more complex kind of a recurrent neural network, like, for example, an LSTM. You might have heard about that from Professor Fauser, I don't know. So a long short-term memory net, which has some more components, but in general, it's a neural network and it's recurrent to some extent. So we have an RNN here. It has, as an input, it takes the internal vectors, this embedded vector that is kind of the output of the previous one. Then we feed in the word and we calculate the new age and so on. And at some point, when the input sequence is ended, we have an encoded vector, which we can then use to generate a new output. So that is the idea of encoders and decoders. We will see encoders and decoders in a transformer as well. So let's go to the next slide. We will not implement now the RNN because we don't have so much time, and I think it's better to have some fun with LLMs. So that. So let's have a look at transformers. So usually, we have ChatGPT, for example, GPT. The T is a transformer. It's a generative, pre-trained transformer. Some of you have the paper, I think, for study. So transformers are part of the large language models as well. So a transformer architecture, when we talk about architecture, we mean network architecture or topology of the neural network. Right? So transformers are deep neural networks that consists of combinations of encoders and decoders. And for natural language, so they can be used for different purposes, but for natural language processing, they are somehow used as successors to sequence and other kind of recursive or recurrent neural network models in NLP. Oh, it's gone. The idea is what we did now, but what we didn't do, we didn't program the recurrent neural network. If we had done so, we would have seen that recurrent models have some challenges for the training, because you have to be careful how to handle this in the back propagation. When you train it, you have to do usually use back propagation to calculate the gradients. And of course, if a model contains the previous model, and somehow internally, this gets complicated and is also somehow sensitive for more difficult, for more unstable for the training. So to some extent, it's beneficial to get rid of these recurrent structures, especially from a numerical perspective. So the idea of these transformer architectures is to avoid this recurrent structure, but to make the model large enough to take a reasonable long input. Yeah. So the idea is, for these transformer architectures, we don't train the model on a arbitrary length sequence, but a very long sequence of a fixed size. Yeah? And this is achieved by making the model larger, so it can kind of handle this large number of inputs, this input window. So we have kind of a batch or a input window, as we have done with our word2vec. So you have a text, and then you define an input window of a certain length, 5 tokens, 100 tokens, whatever, and you shift that to the text, like we did with our word2vec. So the input and the output now are of fixed size again, and then you can, of course, we all know that this window is bigger than 5. In ChatGPT, for example, you have input tokens, about 1,000 tokens. And of course, to have thousands of tokens in the input and in the output, you can imagine you need large neural network models, and much larger than the recurrent neural networks. And the second thing that has been added in this transformer architectures for NLP is this positional encoding and attention. So positional encoding means, if you think of a sentence, it's not irrelevant at which position the word is. So if you think of a text, see it? So let's think again, the black cat. The black cat, ears, and so on. So if you think of our test sentence or any sentence, of course, the distance. Let's say this is the cat. So if you look at the distance here, if the text is longer, imagine the text would be longer. Of course, words more close to the cat, for example, more likely relate to the cat. So the black is usually an adjective is somehow before or after or something. So if it's 100 words later, it will probably, and the cat never appears again until then, it will probably not have to do too much with the cat. So distance is something. So for each word, you could try to get some, let's say, importancy that declines so farther you get away. So that is, and of course for the black as well. So you have for every word, you have some kind of positional encoding, which means that that the model takes into account the relevance in terms of the distance, somehow smoothed by some sine or cosine function to actually somehow modulate the importance in training. So that's positional encoding. So in addition to just, we know, so the approach is first take the text, convert every word into its embedding vector, which is typically obtained by a word2vec or something like that. Now you have a vector for each word. Now you have to, now these vectors are kind of multiplied with some weight to make them weaker depending on the distance. That's one thing. And the other thing is not only the distance is taken into account, but the model is built in a way that it learns iteratively the relevance of the words by some kind of coefficient metrics. And this is what we call the attenuation mechanism. And that actually was the attention mechanism. And the attention mechanism, which tries to understand from a sentence that, for example, for the cat, tears and black are important, and maybe the mouse is important because it's like the cat eats the mouse. So it learns that not every word is the same, and not only the distance is important, but also there might be other factors. So the importance could be learned from the data by training. So there is some kind of mechanism that you say that the model is achieving, that it says, okay, for example, if I'm here, if this is my window position, the middle that we had, what are the importances of the words in my input window? The elements for this word, how relevant they are. That is the attention somehow. So you can look up, okay, for cat, let's look one word here, tears. Probably important, black as well. Maybe the is not so important. So the model will learn that by input out improving it. So it will learn some kind of lookups for the words. And this is basically what we call the attention mechanism. We will have a look on that. So in this combination of multiple transformers, in combination with this encoding, positional encoding, and an additional, let's say, more intelligent attention mechanism that tries to learn the relevance of the words, like look up from the text, is the foundation for the large language models, all of them models. So this is a nice picture that shows a little bit how it works. So you can imagine that these transformer architectures for the large language models, for example, they consist of a sequence of encoders. So it's got, maybe I take the other contact. Maybe better. Show the screen again. Let me share the screen again. Where's my slide? Okay, so yeah, so it's an input sequence of encoders. So if you remember the scheme of the sequence to sequence, or the, let's say, the classical approach, you had a certain number of RNNs for the encoding side, and then you had the vector, then you had a certain number of RNNs for the outcoding side. This is basically similar here, but it's limited. So you say you fix it to a certain number. In this case, it's 6. So we have 6 encoders and 6 out. Of course, in practice it's more, but that's the idea. So we encode, and then feed it to the decoder. This is basically similar to the structure that we had before in the classical encoder decoder scheme, but it's fixed. Yeah? So we fix it to a certain number of encoders and decoders. And so we don't have the problem of the infinite, or not infinite, but very large recurrency in that. So you could think of this as the transformer, the blue box. Yeah, it has a certain number of encoders and decoders, and then it produces some output. So in this case, it is the example is the input is translation. So je suis étudiant, and I'm a student. And in each encoder, so every of these boxes here, you can think of it is a combination of self-attention and a feed-forward neural network. Simple, plain, standard, fully connected feed-forward neural network. So nothing special. And the self-attention is the interesting part. This is the mechanism that actually uses this kind of lookup thing to understand the relevance of words in a certain distance, or not of words in general, but of each word in a certain distance. It learns this, so it's called self-attention because it's not given, but it learns the relevance from the data. So the encoders and the decoders themselves are quite straightforward. They are basically feed-forward networks combined with an attention layer, attention component. The attention component is not a real neural network because it's not. It's more like a linear transformation. We will have a look on that. So the attention component. So this feed-forward is a feed-forward neural network, nonlinear with all the standard activation functions. The self-attention is a bit simpler. Okay, so that's basically this link, and I found this very nice. I hope it's still there. Yeah, it's because it's very illustrative, I think. And it tries to explain how this mechanism works. So once again, this is a bit simplified view. There's an input sequence, which in this case it's a French sentence, and an output sequence, which is in this case an English sentence, but it could also be text input, and continuation of the text doesn't matter. As I said, it's basically what you use for training. So then the decoder is basically the same. No? But it's important that, so the structure is always the same, but they have, of course, separate weights. So they are, as it says here, encoders are identical in structure, but of course it's not the same. So each model, each step has its own coefficients, weights in the model. So it's a separate model with the same structure. And this already shows that the number of parameters of weights in the models is huge. But you see that encoders, decoders, and each of them is a neural network plus attention layer. And the neural network is, of course, also large, depending on the input size and the output size. It looks very, very neat here, but yeah, of course, you must imagine that in practice, it's not only 3 words, but hundreds, yeah? And the same on the output side. And encoders, of course, even if they have only, let's say, it's a simple deep neural network with one hidden layer or so, yeah, the number of coefficients grows enormously. Yeah? You can, that's here, self-attention. Okay, so now we have to look at, and that's, I think, is the interesting part. Now we have to look at this attention layer, which is, of course, the magic. The rest of the encoder is a simple feed-forward network, so that's nothing special. It's just a lot of them. So what's new about it? What made the big difference to for the power of, or the quality of the output that LLMs make LLMs so surprising to us, looking intelligent somehow? Which of course they are not. I mean, this is not intelligence, it's just learning from data, producing data based on the data that you have. But due to the number of, or the size of the data and the size of the training and the coefficients, these models can do high or produce high quality output, and it makes them, this is what makes them so impressive to us, why we are so, many people are so excited that this will replace everything. Yeah, so it's, of course not, but you should always know when LLMs can do something good and when you don't. But anyway, the magic or the quality of the output is, it's not magic, but the insight that made this system so successful is the attention layer. You know? So combining these things, attention, decoder was the foundation for producing this high quality. So the first thing is we need an embedding algorithm. You know that, for example. So the first step is every word is encoded by a vector. In this case, it's 4. Here said, okay, of course, in practice it's larger. It might be 512, for example, for word to vec, which is a good size. So each word is encoded into a vector representing its semantics. In this example, these vectors x2, x3, they are represented by 4 values, of course, to make it more easy to understand. It's not, of course, 4 is too small for practical purposes. So that's our input. The input is encoded into vectors, as we always do. Then we have done that ourselves as well for our last examples. So then let's continue. So how does a single encoder is set up? So you have the input side for each self-attention layer. We have the original embeddings from the words, input, which are fed through the self-attention layer, producing a new intermediate vector Z, which is the same size. And that is then fed into the feed-forward. So that's the structure of one of the encoder boxes. The others look the same. Okay, so now let's continue. So that's the first step. Remember the Z's and the X's in self-attention. And as you know, each encoder here, we're not mixing up the parallel strings. So each word is going here, and each word is going here. So the feed-forward network is not mixing up the different words, or the different topics. It's basically just a feed-forward network producing what is that? So the feed-forward layer consists in practice not of one big layer, but one big neural network, but of multiples for each parallel. For each parallel stream or parallel word, let's say. The actual mixing of relevances, so how the dependencies between the words are reflected in the self-attention layer. And this now goes to here as brackets. So here you see what we are looking at. The self-attention tries to understand the relevance of words to each other. Yeah? So the question, if you take this sentence as an example, what is it referred to? The street or the animal? This is for a human clear, but for a machine, not. So that is something that you have to learn from. So the relevance of the word is not only dependent on its position or the distance, but it might be even ambiguous, especially if, in this case. And of course, it might have there might be references to a longer distance. So that's the interesting thing, and the attention layer tries exactly to mimic that. So it tries to learn from the data that this it is probably more relevant to the animal. Like in an example, of course, for the other words, always the same. Learning that part of it. So this is interactive. I think we can. No, it's not. Okay. I probably have to open it. So now let's have a look how this works. So that's actually the scheme. The authors of this self-attention mechanism introduced three terms or labels for these, let's say for these coefficients or these matrices, queries, keys, and values. Yeah? And so we start with some embedding. It's our X, so the embedding that we fed in. And then we have queries, the keys, and the values. And each of them can think of there is a query for each word, there is a key for each word, and there's a value for each word. So they form a matrix. And the matrix is of the size, so these are vectors, okay? So they are labeled queries, keys, and values, but in fact they are just vectors. And they have a certain size, which might be different from the size of the original embedding. So we end up with matrix. It's 3 times 4 because we have 4 words. In this case 4 because it's 4. Yeah. So this is like Q1, Q2, Q3, and so on. And this is the word. And yeah, in this case they are all 3, but the structure might be different. So in the end, we can put this into matrix form. So they're abstractions that I use for calculating and thinking about abstractions. So if you think of this example here, what's happening? First of all, we calculate a score. And you can see that this is somehow obtained by the query vector for this word times the key for the other. So you calculate this score here, which is just a product of these two. For, let's say, if you have thinking machine something, yeah. So for thinking, the first word, you would calculate the score like that. For the second word, for thinking, from the perspective of thinking, you would calculate it like that. So the query vector is the word that I'm looking on, and the key is the vector of the word that I'm looking to. Yeah? So if you look from thinking to machines, or from thinking to some more words, you would calculate it like that. So this is the score that is obtained. That's the first step. So you try to have a matrix where you, for each word, you weight the other words. From the perspective of one word, weight the relevance of the other words. Okay, what's happening next? Quite easy. It's basically normalized, so it's divided by some coefficient, which is more like experimental knowledge, and then it's put through the softmax function. So this is some normalization to make it smooth. So nothing, no magic here. Is basically numerical stuff. So the score is divided by the square root of the vector size. In this case, it's assumed to be 8. And then it's fed into the softmax function to make it normalized. So now we end up with a normalized score. So this softmax score determines how much each word will be expressed in this position. And so it's basically how the other words for this position, we have a position in the sentence, and how you calculate the relevance of the other words. So the output would be our Z. So now each score is multiplied by some value, which is also has to be learned. And this gives up the Z. And then we calculate the Z from that. That's the scheme. So the original query vector is actually obtained by multiplying. So the original word is going into the query vector, and we have the key matrix to obtain the key vectors. So they are obtained from the input. So we have some input metrics to obtain these. So they are not just random. They are calculated by the input matrix from the X. 3 values calculated from this one, and so on. And then we actually calculate these weights and take the values times the weights. So in this output for each set, we have now, because we sum them up, these are summed up here. So we have now not only the word itself, but also the influence of the other words around it. So that's the idea. So each word, so that represents thinking, but not the pure thinking anymore, but with a mix-in of weighted of the surrounding words. So each word is set into context, basically. So it's all about context. It's about learning, okay, how the other tokens around are kind of affecting one word. So the input here, the Z now, is basically a representation of thinking, but in the context. You must imagine that even already the embedding, the original embedding, which is learned usually using word2vec, already contains semantics. So it's already knowing something about the surroundings, but in a fixed way, only for a word, not depending on the concrete actual text. And now we have this learned for each text. So this is a calculation that basically mixes in the other words into the representation of this word. So the first step is you have the inputs, multiplying them, creating these K, Q, and V vectors, and then we calculate just using the softmax as that. So that's the calculation. That's a simple attention layer. So that's not multi-head attention, but a single-head attention. We just do it once. Now, in the large language models, to make it even more complex, we do it multiple times. And then, at the end, we concatenate them to a larger representation and mix them together again. So what we, this is the multi-head attention. The multi-head attention means you do it multiple times. You have this mechanism with the Q, V, and thing. Do it for each word, but do it multiple times. And then at the end, introduce another matrix of coefficients that combines this again. So you increase the variance and the variability in the model. Basically, that's it. Okay, and through this mixed matrix, this is W0, you would have obtained multiple Z's, and then you mix it into to get a new C again. Combines them. Yeah, so that's just adding another layer of coefficients. But basically, this transformation is more or less linear, so there is no activation function. So the whole attention mechanism is also a linear. It's basically a transformation similar to a neural network, but linear. So it's not really. It's not like a neural network where you have some we can imagine the attention mechanism is somehow a linear transformation put in front the nonlinear and being able to understand better the coefficients. So it's a handful of matrices. That's not more. It's basically just matrix vector multiplications. Here it is summarized again. So you have paddings of input. And then we split that into multiple attention. We calculate that in the sense that we have the three matrices for each vector, but multiple times. So for each head, they call it a head. So this is multi-head. If you would have one single head, then you do this nice calculation, obtaining the intermediate Z vectors, and then you mix them together by another big matrix to get this one. So that's the structure. You can program that. It's not magic. It's not so complicated. It's basically just a lot of coefficients. Using PyTorch, we have learned how to program a linear transformation now, so we could basically write it. So they put XOR instead R because the second and third and so on encoder, of course, gets the output of the first one, which they denoted by R. So this is either the original X, which would be the input at the bottom, or the R's, which is the input from the previous layer. So if you look back here, beginning. So they call this R. So that's for the second and third and so on encoder, the input is called R, not X, but it's the same length. So it's a vector. Each encoder has an attention layer.
Yes, no, the R is a hidden layer?
No, it's a vector. It just represents the intermediate representation of the word. Yeah? So it's not a layer, it's a word, it's a vector. So at the bottom, when you start with the first encoder, you have the original text encoded in embeddings. But after you fed it to the first encoder, it's not the original vector anymore, it's something new. And for the second, which has the same structure, this is used as the input. So the second, third, and so on get the output of the previous one. So yeah, it's not the X anymore, they call it R, it's the intermediate representation of the word.
Thank you.
Okay, so that's basically all. That's basically all what we need to know about attention. Yeah? And yeah, that's what large language models do. So this is the structure of a large language model. So it's a neural network with some additional linear transformation to handle the attention. And also in the beginning, some positional encoding, which we omitted for simplicity. But that's the basic idea. Okay, it's more like an experimental finding that this works. So people had approached this stepwise experiment. We need to see and learn that, for example, attention is beneficial for the work. And the rest is just making the models bigger. It's not completely true. I mean, there are now some, let's say, more smart approaches, like DeepSeek is using, where we have not just using one big structure like this, but multiple small, having another, let's say, kind of model in front that actually switches which path is chosen, which makes things smarter in a way. It's smaller. So so there are some architectural improvements as well. So it's not just making the model bigger, but to a large extent, it's basically making the models bigger right now. And the question, of course, is if this is, I mean, humans always think it's linear. So you have an approach that produces phenomenal results and it seems intelligent. So let's make it bigger. At some point, it will be as smart as we are. Yeah? This is wrong. Because just making the model bigger is not necessarily making the outputs better in any case, because there's there might be some overfitting, there might be some situation where they're making the more coefficients, doesn't make it better, but just maybe harder to train or something. So it's not that just, to my opinion, it's not that you can extrapolate this to infinity. And the question is, the design of the model is made for a certain purpose, namely to create sequences from sequences. So if you want to have different problems or solve different problems, might not be the best. For example, I had an interesting, attended an interesting presentation last 2 weeks ago on a conference from some colleagues from Magdeburg. And they investigated the possibility to understand sensor data from machinery using LLMs. Can we use it to learn and maybe predict what happens, will happen, and so on, to make some kind of predictive maintenance? And the results were really poor because LLMs are not made for that. It's the wrong problem for an LLM because it's not a general. They tested it. They wanted to show basically also that it's the wrong tool. Yeah, to see that LLMs are not the solution for everything. Yeah, I said, okay, this was expectable. I mean, the model is not made for that. And they said yes, but we wanted to demonstrate that because everyone at the moment is saying LLMs are so high. And you would have much better results just using some kind of standard autoencoder or whatever neural network, not such a LLM. So it's like a
It's just that you don't think making it bigger is the solution. So what is, in your opinion, the better approach, or maybe it's smarter if you don't make it?
You have to improve the design and the architecture of the network. Find new components. The problem is that the human brain is still working different. It's not an LLM, a large LLM. So it has, for example, the possibility to reorganize itself. So synapses, they are biological processes, and it's not static. It's plastic. It's plasticity and so on. So there are many aspects that are not coming from neurobiology that are not reflected in our current neural networks. So I think for new problems or to increase the quality, we will have to have like the attention. So at some point, people say, okay, realize that this attention mechanism obviously makes it much better. It's not just a linear set, it's a huge improvement. And if we will try to have something else like that. It's not. It's an architectural thing. It's not just training and making it bigger. Because the capability will not increase. That the fundamental capability of this model is now defined by the structures, and this works, and this is nice, and it can solve some problems, but it will not solve new classes of problems necessarily. So it's not a general artificial intelligence. It's just a huge neural network detecting patterns and producing patterns. And so if you want to move on to more to other types, so intelligence is a very complex thing, and it has to do with interaction with the environment, for example. A human brain or any brain of any animal learns from interaction, which these models cannot do. They just learn from text, or some pictures or something that we feed it. So it's a very reduced point of yeah, we have to have new model architectures that we cannot maybe imagine now, because if I do, then I could write a paper about it and do it. But it's I think it's not, and this is also what DeepSeek showed a little bit. Yeah, it's not about always making the model bigger. It might be better to think about some clever design. Yeah? So, and of course, still DeepSeek is just an LLM, and of course, many things can be, or applications can be designed by improving the let's say the architecture of the whole application. So we can have multiple networks, we can have agents that collaborate, and so on. So this might produce very smart new applications, but it still is not intelligence in a human sense. It's just better architecture. Here they explain a bit about positional encoding again, but that's basically, yeah, we have some normalization layer in between, and normalize, it's just numerical stuff, and so on. This is about details. Right? Now let's look at the decoder side. A short look at the decoder side as well. So that was the basis of the attention mechanism. So at the end, we have these now, we produce these R's, and then we feed them in the decoder. So we have a different attention mechanism here. So we create this, so from the output, another key and value vectors are produced. It's not new. And then fed into all the decoders. This is an animation, as you can see. It uses this. It has only two encoders and decoders, so now we have that. We did with the decoders. First, second. Now the output is fine. No? You see? After finishing the encoding phase, we get a decode. Each step in the decoding phase outputs an element from the output sequence. No? So each step produces, first iteration produces the I. So let's see again. So that's the input, we feed it in. Now we have the R's obtained. Okay. Another K and V vectors are calculated. Now here, so the suffix. Now we receive the I. Now the same input is done again. So now we have the decoding times 2. So now it produces the words. And that's the structure. So it gets all the input, feeds it every time through the encoders. But the outputs also take the output as an input. That's a typical situation. It's like in our language model. We take the previous words and then say, okay, what's the next one? Yeah. Sorry, what? What is what we're doing by No, this is just an example. Yeah. So they just make it simple enough to show you on the screen. So we have some input text. In this case, it's French, and we have some output text. It's English. Of course, they are not of the same length because words are different. And we need the F in English. In French, we don't need it. So that's 4 words. And yeah, we just said it's equal. So this is just a very simplified example to illustrate. But it shows the structure. So what it does is you have an input. It's your prompt basically, and all that prompt context you feed in, and then it generates an output. And in this output, it uses the previously generated word also as input, like our very simple probabilistic model did. Yeah.
The number of encoder and decoder depends on.
It's basically it's a hyperparameter. You can choose that, and it's not probably not 6 but more. Yeah. Depending on this is why the models are. So number of encoders and decoders is I don't think it has even to be equal. It's not so important if it's equal.
When we increase the encoder and decoder, it makes the system maybe more complex or.
Yeah, sure. The more encoder and decoder boxes you have, you must imagine each encoder is a smaller network or a set of networks plus an attention layer. So if you make the number bigger, you get a lot more options. So with each encoder, we just call it encoder and decoder to let's say divide the model into building blocks. But in fact, of course, because they are all combined, in the end, this is just a huge transformation, a huge network. But of course, to make it more understandable, we break it up into let's say smaller components, called encoders, decoders, and so on, which again consists of smaller components, which are the decoder network, attention. And this is why in ChatGPT or in any of these models, the output is always produced stepwise. So it's not just the output, but it builds up over time because it's iterating through that. Okay. So this little animation should illustrate how the model builds up the text. Okay. So I think the next thing we will do now today, maybe on the next week, is so we could program that, but that's of course a lot of work, and we cannot train it, so it's not so much fun. I think it's more interesting maybe to see how we can use LLMs in practice. Yeah, as we now have basically understood how this model works and what we're actually doing. And to do so, we can, of course, we can go to ChatGPT, but that's not itself. I wanted to show you how we can make use of different kinds of LLMs, also in local installation. Of course, in practice, you would not do it on your laptop probably, but on, let's say, some bit more powerful system. But for example, on this MacBook, you can even do something useful. It's not super fast, but for daily purposes, you can have a local LLM as well. So how we do that? So people often ask, okay, how can I use LLMs? And you might know that many LLMs are trained, ready-made LLMs. So it's a model with all the coefficients. They are already open source, so you can use them freely. Like for example, from Meta, we have the Llama series of LLMs, which we can use freely. And DeepSeek, for example, you can also use ChatGPT. Not all of the models, but the newer one not. But many of these models are now freely available, so we can use them and play with them. And to do so, we need some kind of infrastructure. And there's a nice framework which originally was designed for actually using Llama, but now it supports basically all these models, and that's called Ollama. So you see, you can run a lot of models. And yeah, you can download this infrastructure here, run it locally. This is basically the infrastructure. It's a component that allows you to run various kinds of models that are available for download in an easy way. And well, that's basically the idea. So I recommend you to install it now. And basically, when you have installed it, should not be so big as it is basically the infrastructure, you end up with a Llama here. You don't see a lot of this tool, basically. It's just here. There's the Llama. Now we have a Llama. Basically, you can start it, and that's all. Okay, so was it successful? It's downloading still? Okay, that's good. No worries.
I have to like do some journal.
It doesn't work, or?
I have to do it on journal like so not journal.
Yeah. That's the basic version is on terminal. I will just show you how you can set up a UI as well.
It's not working.
But if you download that, then basically you will end up with something that's running in the background. You can use it on terminal.
So I like down.
Do you have? Maybe you need to run it from applications.
I did.
Do you download it?
It's here, and then I clicked on it. It says go to applications, so you should have it.
Yeah.
But it's not running.
It's running exactly. Now it's running. That's fine. That's all.
That's it.
It's running in the background. Yeah, you have it here. It does not have a lot of UI. Because basically, it's basically like a Docker or something. It's like an infrastructure running in the background. So now you would have the Olama command here on the command line. Right? You can interact with this process using command line interface if you have installed it. Or I will now show you how you can run a UI as well. Yeah?
Okay.
There's a web UI for it that you can run.
This is the way you can access it. Like here.
Yeah, you can access. You can do everything from the command line. Yeah. And but you can also use the UI to have a more like ChatGPT-like experience.
Thank you so much.
So after you've installed it, you basically see nothing, more or less. That's the problem. It just started. So it's like Docker or something. It's a daemon process running in the background and providing the infrastructure. Okay, so don't be scared. But what you have now to test if it's installed, if you go to your shell or to the PowerShell in Windows, you can now use the Olama command. Let's test it if it's there. Basically, it shows you some help if you just call it Olama. So with this command, you could now, for example, download models and start a chat and so on with the model. But that's not what, I mean, we can do it like that, but it's, of course, a bit text, let's say, not so flexible. So let's also think about installing the UI. And actually, the UI works as a Docker container, which is easier to install. Let me start the engine. Okay, I've deleted it. That. Let's see, there's Open Web UI, that's it. Yeah. So let me explain. So this is the Docker command. You need to start it. I will put it in the chat. But please don't let us first discuss it before you use it, because we have to adjust something. No, it's not. I need to. So let's do it again. So. So this is a command line command to run it in Docker, okay? And it will download the thing. It's called Open Web UI, which is a free UI for Llama. And the only thing that has to be customized is actually the Web UI path. So this one. So this part after the Open Web UI, this part here, which I mark in red, is a path, a file system path. And of course, this uses Brune is not working for you because it's my computer. So you have to adjust it to your location. So what it does, it basically refers to, so as you can see, it maps a volume. It maps a volume under the label Open Web UI into the container and mapping a local host path. That's the host path where Olama stores its models. It's basically for interaction, so that you can choose a model. So in this directory, Olama, when it's running, it's a working directory of Olama, and that stores the models that you download, the LLMs. So you should first check where this is on your machine before you run this command. Clear? Okay, good. So I will just start it, but now because for me it works. But so first of all, before you run it, let's find out where your .olama folder resides in your file system. So it should be typically in your home directory. So on the Mac, just type CD or in a Linux box. And then you have this .olama here. And there you have nice stuff. Yeah, let's see. And there's a models folder, and inside there should be a models. So this is kind of the configuration directory of Olama. Please find out where this on your computer is. In Windows, it's typically also probably in your users directory. So we go to PowerShell or to the shell in Mac, you should find out where it is. And the path to it, the absolute path, is what you put here instead of this one, because that's mine. It will not work for you. But the rest of the command should work. The only thing is, as you can see, it wants to use the port 8080. So make sure that it's free. And 3000, so that is free. Where to? Scroll down. Why? There's nothing to scroll down. It's just. So next step, find out where your .olama folder is. And then paste it in the command so that we can access it. You have it? You will start the Olama. Okay, yeah, that's good. No, you should just have to put the open web.
Oh, I did again.
Yeah, let me. You have the it's -v open -w double dot. That's the internal name. That probably should be there. But the rest, of course, works. So you can stop it again and run it again with the.
I'm sorry.
Yeah.
Which one?
Here. After the -v, you need to put the open web.
Oh, you're absolutely. Sorry.
Yeah. No worries, but let it complete download because it doesn't change. It's only configuration change, and then stop it again.
Okay. And then I open.
Yeah. Friends, are you working interactively?
Yeah. I installed a Olama shell.
Yeah.
I want to tweak it to the normal terminal.
Okay, nice.
Yeah.
Send the list. Okay, yeah. Okay, so you want to file /files.
Same.
It's a puzzle. Hack.c.
So
Okay, yeah, it works like that. I mean, you just use it locally with the command line. It's fine.
Does it totally locally?
It's totally locally.
Yeah,
You download the
no, can work offline.
Yeah, it runs Llama 3.2.
So it's like 100 gigabytes and
Yeah.
yeah.
Exactly. It's a small one. Yeah. But you can use it locally. Yeah, it's cool.
But are they updating these data inside the module?
No, you have to download it again to update. It's not automatically updated. You have to download a new version, plus new version. Now you're completely local. It's yours.
Yeah, I got it on the lab instead of I can't install it, but it was my.
Okay, yeah, okay.
I already.
Yeah. Yeah, so you have to change this part. Let me change dot. That's the dot. So after you run this container properly, just let me show what you should get when it works. You have a Windows, ChatGPT-like web front end locally. So you can access it through the browser. And it looks like that. I don't know. So it then should make mainly after login, it should look like that. This is running locally. And you can see I have different models here. Now let's just use Code Llama for demonstration purposes. Hallo, wir sind gleich fertig. And now you could ask a question here. And now Code Llama starts answering. And you can see it's not super fast, but no, okay. It starts creating hello world. Let's see. Yeah?
Professor, does it get trained with the input that we give it into the chats, like, and also does it retain the memory?
Sorry, what?
Does it get trained with the inputs that we provided to it? Like, let's say, for example, with the ChatGPT, we
No,
tune
no,
it.
no, no, no. It's a local, so it's a local open source model. You run it on your computer. It's nothing. It's not retrained anyhow. It's just it's just inference what we do. So the model is not trained on your machine, and the data stays completely on your computer. There's no nothing. So this is a very interesting technology for companies that want to use it internally. They don't have the right to maybe disclose things to ChatGPT. So it's completely yours.
No, but the model is trained internally, like on the local host, or no?
No, it's not trained. It's just downloaded as it is from open source repositories like Hugging Face and so on.
Okay.
So Olama is basically for using the models. It's not for training. Yeah.
Keep on showing us on your screen.
Yeah.
So the end of sentence, when does the model decide to reach it?
Good question. So it's at some point it stops. Usually I think it's a sort when its output buffer is full or something. Yeah, you're right. I mean, you can stop it at any time. If you see it starts producing nonsense, you can stop it. Here, stop. Yeah. So now it's no, it's a different. But there is a button to stop it. Sorry. So when does the model decide to stop? It's a good question. There must be some mechanism internally, some heuristics, how they stop it. Because in principle, this works till infinity. It just produces the basic structure of the model. But you need to stop, of course, at some point. That has to be kind of built in, because either it's a limit or because at some point the model, the more you produce, the less good is the result. So at the end, it just starts repeating things, creating nonsense, whatever, hallucinating. So it should stop, and it stops basically. But I'm actually not sure. I mean, there must be some mechanism. As I said, the internal thing is just some limit, probably some output limit or something like that. Do you like it locally, having your own ChatGPT at home?
3,000 is a more.
3,000, part 3,000, that it's not started. You have a different name, but it's another UI, so I'm not sure if it's the same. How do you start it?
Because I was working on this.
Okay,
before.
yeah, that's fine, you can use that as well, yeah.
But how can I go to
I'm not sure, I mean, you have to configure it probably. But know that the Olama is running on your host machine. Yeah, so you need to make it at least able to access the directories, the Olama directory. But I'm not sure how you use that in this UI. But it's basically another software, so you have to find out. I don't know it quite.
maybe
We just use the Open Web UI, then it works like it should. But of course, you're free to find it out, but then you have to Google that yourself. I presume it can work really well. Okay, so does it work?
I'm still like figuring it out.
There you go. At least you can show the screen, and now you have to select the model.
But I still try to do that.
You tried it?
I'm still trying to do that. It's okay. I will.
Okay. Okay, so that was what I wanted to show today. And if you have successfully installed, it should look like that. So you can change the model. You can also search for a new model, and you can also ask it questions. Yeah? That's the idea. So this is fully local. It's fully running on your machine. It's just inference. It's not training the model somehow. So you can just work with it. And yeah, so the advantage of such frameworks is that you can work locally. Of course, PC is maybe a bit too slow for bigger things, but you can use, as a company, for example, you could install that on your GPU server and run it inside using the data for all kinds of applications. Okay. That's what I wanted to tell you today. And I think somebody already came in, so maybe we have to stop now because the room will be used. Okay, so see you all this afternoon for the presentations. Thank you.
Thank you, Professor.
Thank you, Professor.